Welcome back, everyone. We're in Chapter 13 on chemical equilibrium, and we're going to practice using what we learned in the last lecture on using equilibrium constants. If you remember, the equilibrium constant is a capital K with a subscript of a C, and if it's a big number, it's going to suggest that there's lots of products being made. If it's a small number, it's going to suggest that there's lots of reactants that stay reactants, that don't form products. Okay, that you're going to see that the arrow is more to the left if it's a small number. The arrow is more to the right if it's a large number. I want you to start thinking of that. You're going to need to have that concept in the next lecture. So if it's a large case of C, that equilibrium constant is going to show you that there's a large amount of products. So we think of the arrow going right as big and a tiny little arrow going left, okay, or a smaller arrow. If it's a small case of C, you're going to have a large arrow going left with a little arrow going right. Okay, so it's going to tend towards one way or the other. The only other way that I would consider that it would be exactly equal, where your arrows would be equal in size and length, I guess, is if the same amount of concentration of products and the same amount of concentration of reactants. Okay, along with their coefficients. It would have to be something unusual for it to be exactly like that. Normally, it's going to be one way or the other. You're going to either make a lot of products or a lot of reactants. Okay, so we're going to use them now, which means problems. Okay, next slide. So, a container is initially filled with SO2 and oxygen, or is only SO3. Okay, so what's going to happen? So if it's initially SO2 plus oxygen, they're going to bump together and make SO3, which is a product of these two reactants. If you had only SO3 in the chamber, what you're going to see is that occasionally these are going to break down into oxygen. They're going to break apart and you're going to have oxygens floating around. Those oxygens are going to bump into each other, and then you're going to end up with SO2 plus oxygen. Okay, so you can see these guys can form this as a product. This is going to break down into this. Okay, so what will happen is even if I could make all of them products, they're still going to go left. The arrow is not going to go one direction only. It's a reversible reaction. You're going to get some movement to the right and some movement to the left, and then how much product you have is based upon how much eventually net change do you have after all the movement. Is it more towards the right where you get lots of products, or is it more towards the left where it stays reactants and only get a little bit of product? So if equilibrium is reached after most of the forward reaction has occurred, the equilibrium system favors the products. Okay, so if you're making a lot, here's initial, okay, and if at the end you're going to end up with more products than you do reactants, then it's favoring the products. Okay. Conversely, if you're going to have more reactants at the end, okay, so you have a small case of C, so the products actually break apart back again into reactants, then this will be a bigger towards the left. The arrow would be more towards the left, small case of C. So if you have a very large case of C, okay, so we're looking at large numbers, small numbers. I promise you that I'm not going to give you like a 15. You want something big, 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 or something small, small, small. So you're going to have something to the big power, or you're going to have something to the negative small power, something like that. Okay. So a reaction with a large case of C produces a large amount of products. Okay. Very little of it remains as reactants. Okay, so here's an example where you have a product and you take this is all done from the lab. I don't know what these numbers are. You'd have to measure it. So whatever the molarity at the end of the experiment was, times the 2, in that case it must have been a coefficient in the balanced equation. In fact, I could find the balanced equation. Watch this. This is N2, and it's going to be 1 N2. Because there's nothing here, so that's a 1, plus 3Cl2 yields, and I'm going up here, this is the products, 2 NCl3. I really hope you saw that. Can you see it? I can find the balanced equation by going backwards from the K sub C. Okay? Now look at this number. 3 times 10 to the 11 means it's 3, 2, and 10 zeros. That's a huge number. That's an enormous number. That means it's going to be a big K sub C, and most of the stuff at the end is going to be products. Okay? All right? So a large K sub C products. You thought I cheated. I didn't. I went from here. I didn't even look down here. Do you see what I did? N2 is to the 1 power, so it must be 1 N2. Cl2 is to the 3rd power, so I'm going to add them. They're multiplied here, but I'm going to add them in the balanced equation. Take this as the coefficient, 3 Cl2. Then I'm going to yield, and now here's the products, NCl2, but I'm going to put a 2 in front of it because this is showing me that that's the coefficient of the balanced equation. Okay? When it reaches equilibrium, when it stops changing, when the numbers kind of equalize, it will essentially consist of product. Very, very little reactant will be left in the jug. Okay? If equilibrium is reached after a very little forward reaction has occurred, okay, meaning very little product is made, then the equilibrium favors the reactants. So you're going to get a huge left arrow and a very little forward arrow. Okay? So here's the initial concentrations. If at the end of equilibrium, when everything's over and nothing's changing anymore, so it looks like everything's finished, these two guys are still reactants and a tiny little amount of product is made. Okay? Or if you start with the NO and it breaks apart mostly into reactants and only stays a little bit of it as products, then it's going to be a huge left arrow and the K sub C will be very small. So let's look at that. Okay, so here's a different example. I'll come this way this time so that you don't think I'm cheating. This is 1 N2, which means this is going to be on the bottom. The left is on the bottom. The right is on the top. Let's start at the top. Concentration of NO, that's what the brackets mean. Taken to the 2nd power, that's because that's a coefficient, 2. Divided by, now I'm in the reactants. It's plus in the balanced equation. It's multiplied in the K sub C expression. Concentration of N to the 2 to the 1 power times the concentration of oxygen to the 1 power. Okay? Now, I don't know what these are. This is from measurements. This is from the lab. I would have to be told these things. I'm not born knowing these things. Okay? I don't know what it is. But if you tell me what those concentration is, I know how to use my calculator enough to solve this. And I look and I get a tiny number. This is to the -9th power, which means I'm going to move the decimal place 9 places to the left. And I'm going to have a decimal point, and 8 zeros, and then a 2. That's a tiny, tiny little number. Okay, so if you have a small K sub C, you're going to have a huge, and I think that's what this is, huge left arrow, and a teeny, teeny little right arrow. Okay, so at the end, when it reaches equilibrium, it's going to mostly be reactants. Okay, very little product. In the jug, almost no products made. Almost everything stays as reactants. Okay, so here's the summary. A reaction that favors the products has a large K sub C. Okay, products is a big number divided by a small number. Okay, products are on the top. The reactants are on the bottom. So if you have a big number divided by a little number, you've got a big number. So K sub C is big. It'll go towards the right. Okay, that's the idea. Go towards the arrow. The bigger arrow is towards the right. If you have a very small one, that's down here. If you have a small one, then it's going to go towards the left. Okay? But if you have one where it's close to 1, what does that mean? Anything divided by itself is 1, which means if the numbers on the top of the fraction and the bottom of the fraction are essentially the same, then you're going to get just the same amount of reactants at the end and same amount of products. Half of it will be products, half of it will be reactants. And you're going to end up with a K sub C, which is about 1. That means that it's essentially the same concentration of product and reactants at the end of the game. Okay, so here's some examples with large and small K sub C values. So I've got carbon dioxide and oxygen yields, or carbon monoxide and oxygen yields carbon dioxide. 2 times 10 to the 11, what would it be? That's a huge number. Big Kc, it's going to go to the right. Okay, go to the right. If it heads to the products, I'm going to say it goes to the right. This guy, let's look at the K sub C. It's still big. Do you see? 1.1 times 10 to the 7. 7 zeros. Okay, actually 6 zeros after this. So it'll go to the right. Okay, so look at this one. 10 to the 2. Okay, it's not 1. See, it's a big number. This would be 160. See, 160 is bigger than 1. So it's going to go to the products. It's not as much products as these guys. These are almost entirely products. But there's more products than reactants at the end. So it's going to go towards the products. Okay? Maybe weakly, but it'll still go towards the products. These guys, when I get it, I've got a small number here. This is a decimal number, so this would be like 0.0 something. So that's small, it's less than 1. So I'm looking for a negative exponent. If it's a negative exponent, it's going to go to the left. If it's a 1, they'll both be equal. If it's a positive exponent, so if you have a 0 exponent, if it's 10 to the 0, then it'll be equal. It's not going to go to the right or the left. You'll have exactly the same arrow going both directions, same size. But if I have a positive exponent, it's going to go to the products. And the bigger the exponent is, the more entirely it goes to the products, the less reactants that you have. Conversely, if you have the smaller or the bigger the negative exponent is, the smaller amount of product is going to be made, and most of the stuff is going to be reactants. Okay? So this looked scarier, but it was actually a fast lecture. I hope you understood. See you in class.